Hello and good day each and everyone. I am a student from Nueva Ecija University of Science and Technology, San Isidro Campus, and my name is Kennette Banal from BSE 3B, major in Mathematics. And for our task in SEM 12 this week, we are asked to choose a lesson and create a video presentation about it. And now, let us start. This video lesson is all about Wilson's theorem. But before we proceed on our topic, let me introduce to you the history of Wilson's theorem. Wilson's theorem is named after John Wilson. As you can see in this slide, here is his photo. John Wilson is an English mathematician. Also, he is a student of Edward Waring. Wilson's theorem history. Ibn al-Haytham around 1000 AD and John Wilson about 1800 AD both asserted this theory. In 1770, Edward Waring presented the theory, but neither he nor his pupil Wilson were able to verify it. In 1771, Lagrange presented the first evidence. There's evidence that Leibniz knew about the discovery a century before it was published, but he didn't publish it. Now, for the main topic, Wilson's theorem. It states that a natural number n is greater than 1 is a prime number if and only if the product of all the positive integers less than n is 1 less than a multiple of n. That is using the notations of arithmetic modularities. The factorial n minus 1 is equal to 1 multiplied by 2 multiplied by 3 multiplied by 4 and so on and so forth multiplied by n minus 1 satisfies n minus 1 is congruent to negative 1 mod n. To further discuss Wilson's theorem, if n is a prime number, then n minus 1 factorial is congruent to negative 1 mod n. And here is the proof. N minus 1 factorial is equal to n minus 1 multiplied by n minus 2 and so on, multiplied by 3, multiplied by 2, multiplied by 1. And here is the strategy. Pair each number with each inverse. And also, there are exemptions. X squared congruent to 1 mod n. We equate both sides with negative 1, so we have x squared minus 1 is congruent to 0 mod n. To factor x squared minus 1, we have x minus 1 multiplied by x plus 1 is congruent to 0 mod n. For case number 1, x minus 1 is congruent to 0 mod n means x is congruent to 1 mod n. For case 2, x plus 1 is congruent to 0 mod n, and it means x is congruent to negative 1 mod n, and can be alternatively said that x is congruent to n minus 1 mod n. These are the two exemptions of this theorem. 1 and n minus 1 are their own inverses. So now, let's go back to n minus 1 is congruent to 2 multiplied by its inverse, which is 2 raised to negative 1 multiplied by 3 times its inverse 3 raised to negative 1 and so on times 1 multiplied by n minus 1 mod n. And it is congruent to 2 multiplied by its inverse is 1, 3 multiplied by its inverse is also 1, and multiplied also by 1 multiplied by n minus 1 mod n. and it is congruent to n minus 1 mod n, and n minus 1 factorial is congruent to negative n mod n. And another example, for each of the values of n from 2 to 30, the following table shows the n minus 1 factorial and the remainder when n minus 1 factorial is divided by n. In the notation of modular arithmetic, the remainder when m is divided by n is written m mod n. The background color is blue for prime values of n, gold for composite values. And that is all for my topic. Hope you learned something. Thank you for listening. Keep safe and God bless. Goodbye.